Okay, so today we're going to continue our discussion of organic molecules that you need to know for this course. And this is the last one, really, last functional group we're going to discuss, and it's going to be esters. We will introduce nitrogen later, and it's of lesser importance for this class until we get to discussion of proteins and such. But this will be our last major group, especially for this test. And I've seen this problem before at the top of the screen. It's sort of a joke now. When you write fluorine, I know you get used to writing chlorine as Cl, but fluorine is not Fl, it's just F, unless you intend to mean a fluorobenzene or something like that. So don't do that. So what are esters? So they're pronounced Ester, not Easter. Those are holidays. Ethers mean something different, so make sure you pronounce them correctly and write it correctly when you give your answer. But esters are derivatives of carboxylic acids. This is what we talked about last time. Remember a carboxylic acid, like this example here, right? It has a carbonyl and an OH on the same carbon. It's a carboxyl group. And it resulted from the oxidation of an aldehyde, which of course was an oxidation from a primary alcohol. What we're going to do now is combine this carboxylic acid with another alcohol to make an ester. Right? So let's talk about the nomenclature real quick here. So this is a carboxylic acid, right? As this example here is one that has 3 carbons in it, but it could be any carbons long here. If we remove this H here, since it is a carboxylic acid, that means this proton can dissociate, right? So that's what acids do. They dissociate their protons. And this H, when it leaves, does not take any electrons with it. Right? The pair of electrons that are being shared between the O and the H and their covalent bond, so there is a bond here, just not drawn. Right? When this proton leaves, the nucleus of the hydrogen leaves, it leaves the electrons behind. So this oxygen, instead of having 2 lone pairs like it does normally, will have 3 lone pairs, and of course a negative charge. The proton that left will be absorbed by another molecule such as water, right? And then you have what's left behind is called carboxylate. This is the conjugate base of our carboxylic acid after it deprotonates. Right? And then after this hydrogen is gone, if you have something else here besides hydrogen, right, like another carbon chain, it's not necessarily the same oxygen. We'll see that in a few minutes. But if there's something else over here besides hydrogen, it's not a carboxylic acid anymore. So in a carboxylic acid, it must have this C double bonded O and then an OH. It's often abbreviated COOH. That's what that means. But when you have an ester, there's no H here anymore. It's some other carbon chain, at least 1 carbon. Right? So we abbreviate it sometimes COOR. Right? That doesn't mean the 2 O's are connected to each other. It means there's a double bonded O and then an OR on this carbon. And that's what an ester is. And it's made from the synthesis of a carboxylic acid plus another alcohol, which we'll talk about in a minute. Okay, so the simplest ester you can think of, meaning by simplest I mean use the fewest number of carbons possible, where R is not a hydrogen, right? So these R's, not necessarily the same R, but the R is not a hydrogen, where I have at least a carbon on each side. What would be the simplest one you can think of? Right? How many carbons would it have total?
3.
3, exactly. And how many ways can you arrange those 3 carbons and still have an ester?
One way.
Right, that's why it's the simplest. There's only one way to do it. Right, so it would look exactly like that. Right, so it has the carbonyl carbon, the 1 carbon over here, which makes it an ester, and then I said at least 1 here, so that means 1 carbon there. What will be the parent chain of this molecule? Which carbon is most certainly number 1?
Methane?
Well, not the name, but which carbon here is most certainly number 1 carbon?
The carbon
connected
connected to the carbonyl,
Yes,
like the double bond.
The carbonyl carbon, absolutely. So this is number 1. It must start the main chain. So how long is my longest possible main chain?
2 carbons?
2. This is not a carbon, right? We can't go this direction. This carbon's separated from the other carbons. So here we have a 1-2 carbon main chain. And so ignoring this over here for now, what would you call this? This 2 carbon chain that's a carboxylic group.
Ethanoic acid.
It would be ethanoic acid, I agree. If this were just an H, that's absolutely right. But it's not an H, right? And there's no acid here anymore. So instead of calling it ethanoic acid, right, we're going to change the name to this 8 ending because there is no H here anymore, right? So instead of ethanoic acid, what would you call it?
Ethanate.
Leave everything else, just lose the ic acid. So don't drop any syllables. It would be ethanoate. Right, and I'll show you that in just a minute as well. But ethanoate, but then I have to deal with this other thing over here. The common name for ethanoate is acetate. You probably heard that before. Right, but ethanoate is what we're going to go with. All right, and then over here, what is this group on the oxygen?
Methoxy.
It's not a methoxy. What's on the oxygen? We're not naming this as an ether because I've already included both oxygens in my name by calling it an ethanoate. That includes both of these oxygens already. What's just this thing on the O?
It's a CH3.
Which is
A methyl group.
a methyl. So esters have two names. The first name describes the thing on the oxygen. Don't include the oxygen in that name. Just describe the thing on it. This one's just simply a methyl group. The second word describes the conjugate base, this part here, of the carboxylic acid that was used to make this. Right? This is the alcohol part that was used to make it. So we'll go over some naming in just a minute as well, but you want to get you the idea that it has two words. Carboxylic acids also had two words, but the second word was always the same. It was just simply acid. Here, each word means something. The second word is the parent name. That's the carboxylic acid's conjugate base from which this was made. And the first word is the thing on the O, which came from the alcohol I added. In this case, just methyl. Not methane or methanol, but just it's a substituent now of methyl on my acetate or ethanoate. And what if I add another carbon? All right, what would be the next simplest one? How many carbons would it have?
Four carbons.
4, good. And how many ways could you put it together? Is it still just one?
2 ways.
What are they? Describe what they would look like.
So one would have 2 carbons on the right side of the O, and one would have 2 carbons on the other side of the carbonyl.
Right, so you can either put the additional carbon over here, making this 2 carbons long, it'd be an ethyl group out here, and leave this alone, or leave this alone and add another carbon over here, like she said. Both of those are drawn here, so I've added the extra carbon on the right here, or on the left here. All right, and the names of these, again, this one, we're not going to use acetate, it's just the picture I have, but instead of calling it methyl ethanoate, you would call this one what?
Ethyl ethanoate.
Ethyl ethanoate. Right, so you name this thing out here. Right, so ethyl, first word, make sure you leave a space so I can tell it's 2 words, and then ethanoate over here. Right, so these are the ones with 2 separate words we're going to see. The one on the left here is not that. What would it be called? First word is still
Methyl propanoate.
yes, so first word is still methyl. Second word would be propanoate because it's 3 carbons long. The carbons are not connected, so you can't count this as 5 carbons because that's not a carbon. Okay, so there's multiple options here. And if I add more carbons, you see this gets much more complex because if I add a 5th carbon, it could be added here, could be added here and branching it, could make this longer, it could be over here, it could be added here, or make this even longer. So the more carbons I add, the more isomers there are. We've seen this before. If you have a substituent, an R group attached, it happens to be an aromatic ring, like a benzene ring, right? Instead of drawing that big benzene ring over and over, we could just simply write AR, right? So AR is the equivalent of writing R. It just means aromatic ring, right? So if I want to abbreviate a big benzene ring, just write AR. You might see that sometimes in the pictures of molecules. So the simplest aromatic ester is called methyl benzoate. Here's a picture of it. So the first word methyl is describing what?
What's on the oxygen?
Right, what's on the single bonded oxygen, so just like before, it's a methyl group, and that's very common. And what's on this side, this main chain is what? Ignore the methyl, what would this be? We saw it last time. If this were an OH, what would this be?
Benzoic acid.
It would be a carboxylic acid, and what would its name be?
Benzoic acid?
It'd be benzoic acid, right? It's one of the only benzene carboxylic acid I asked you to remember. Right? So it's benzoic acid. But instead of benzoic acid, it's part of an ester now, so we drop that acid ending and call it the conjugate base name, which is benzoate. So this is methyl benzoate. Okay. The first word describes what's on the O, and the second word describes the conjugate base of what was a carboxylic acid. Okay, so knowing these vocabulary words, I want you to try drawing these two things. They take into account a lot of these names I had you remember. So phenyl benzoate and benzyl benzoate. Right, what does this mean? Well, they both have benzoate, so that's the easy part to draw. Let's try this first one together. So draw benzoate first. That looks just like this without this bond here, without this carbon. So just draw this ring. If you want to write AR for this, you can. That's fine. Right, so we'll put this thing here, and on the oxygen, what should you draw instead of a methyl group?
Another benzene ring.
Another benzene ring, right. There's no carbon between the oxygen and the benzene ring. It's just connected directly. It's a phenyl group. Remember, phenyl means a benzene ring as a substituent, whereas benzyl means something different. We'll see that in a second. Okay, so draw your benzene ring where this group was. So instead of this line here, it's a line going to a ring. It's the only difference. And then also I want you to draw benzyl benzoate. Okay, sounds confusing at first, but treat it the same way. The second word, you'll draw this benzoate one more time. And on the oxygen, what do you put this time? What does benzyl mean?
Benzene as a substituent.
So
It's a benzene through a methyl, right?
It's benzene connected through one other carbon, yes. Right, so they should look something like this. You had your benzoate you drew here, and then the benzene ring attached to it. That's a phenyl substituent. But if it says benzyl, we reserve that word to mean a benzene ring attached through another carbon, so there's an additional carbon there. Right, so this is phenyl benzoate and benzyl benzoate. Right, and this is used in veterinary medicine all the time to treat animals for ticks and mites and lice, because it kills those insects. Right, so everybody got these names down? What phenyl means? Reminds you it's just a benzene ring as a substituent. Benzyl means a benzene ring as a substituent but connected through another carbon. Right, it's got that extra carbon in there. This is not a phenyl or a benzyl. It's benzoate. It's the parent chain. It's not a substituent. Okay. So let's see how we make an ester. So here's the generic reaction to make an ester. And all esters are made exactly this way. Right? So no matter which problem you're given, when you're creating an ester, and you'll do a lot of these in lab when you're making all your different scents and fragrances in lab, if you're doing that lab this semester. But you start with a carboxylic acid. What this R means over here is any carbon chain. I don't care how long it is or what it is. Right? It's got a carboxyl group on the end. And of course, you already know this one. It's some alcohol. There's some carbon chain, and there's an OH on it. Right? So this carbon chain is listed as R prime because this R may not necessarily be the same as that R. That's all this means. Right? So this R is not necessarily exactly the same as this one. That's the reason we use the little prime. Okay? So what happens between the two is we lose a water molecule. There it is. We've seen this before. We were putting our sugars together. This time the carboxylic acid loses the OH and the alcohol just loses the H. So this O that's left over in the ester is not the same one that was there originally. Right? I mentioned that on an earlier slide. It's not necessarily the same oxygen, and it's definitely not the same oxygen here. This OH leaves as the water, and this H leaves with it to become the water molecule. This O on the alcohol becomes connected to this carbon. This is much like we made what molecules before? Very, very similar to what molecules we did before.
The hemiacetals and the
No.
acetals.
The acetals, right. So the hemiacetal was it just coming together. We didn't lose anything. But when we made the acetals or the ketals, we lost a water molecule. So it's very similar to that. So it's also a dehydration reaction. We're losing water. Right? So it's called esterification because we're making an ester, of course. And the products are going to be the ester and the water that's left over. Right? Everybody got this reaction now? Because I can change this R group and this R prime to anything I'd like, and it doesn't change this reaction whatsoever. The same thing is going to occur. So if you look in textbooks or online, if you're looking for practice problems or the old exams I've posted, all they're doing is changing these R groups, right? And it might look confusing because the R groups look different, but it's the same basic reaction. The R's are not involved, right? The R is this R through its alcohol oxygen ends up connected to this carbon, and this R didn't get involved at all. Okay, so is everybody okay with how this works? So one arrangement that might confuse you is what if this R was actually coming out here, makes a long chain, is actually connected to this R? Right? What would be the result if these two R's were still part of the same overall chain?
A ring?
I would make a ring because they would still be connected to the same chain. You're absolutely right. So don't let that confuse you as well. If you only see one molecule there, what do I do? Well, this carboxyl group, right, on this carbon chain, maybe down the line, has an OH somewhere. You just have to rearrange it so they end up next to each other like this. And you end up with a cyclic ester in that case. And we'll see that in just a minute. All right, excellent. All right, so we also have the possibility of diesters. We've been doing this throughout the semester, where we talk about alcohols and introduce diols, and then we did aldehydes and diols and diketones. So we're doing it with esters as well, right? So a dicarboxylic acid, which we talked about last time, can actually react twice, once on each end. So I'd have to add two alcohols. So if I add an alcohol to this end and an alcohol to this end, I'd get a diester. In fact, I added the same alcohol to both ends. Everybody see that here? So this OH leaves along with the H from what alcohol did I use?
Ethanol?
I used ethanol, exactly, because there's two carbons here. Right, so I added this plus two molecules of ethanol, one for this side and one for this side. And this OH, along with the H of the ethanol left is water. And the ethanol is stuck through its oxygen to my carbonyl carbon. So all of this is gone. This O is not the same as that O. And this is the alcohol that was added. Equivalently, I did the same thing on the left. This OH left, right? And the ethanol that was there is still here. Its H is gone. It left with the OH to make water, and it's connected to this carbon. Right? So how do we name diesters? Same way we name an ester. We name the ester part first, or the parent part first, what was the carboxylic acid. So this is butane dioic acid, right? 1, 2, 3, 4. So the parent name would be butane dioate. We drop the ic acid and add 8, just like we've done with everything else. Right? But in this case, in front of that, the first word describes what's on the O, remember? But so I need two first words. They happen to be the same thing. They were both ethanols, but if they were ethanol and methanol, then I'd have 3 words in this name. But they both happen to be ethanol, so I can call it a diethyl group, because there's 2 ethyls on my dioate. But if these were not the same, say one was ethyl and one was methyl, then I would name it ethyl methyl butane dioate. 3 separate words. Right? So it's the same rules, nothing new. You're just removing this OH, adding the alcohol, and using it as the word in the first part of the name.
I have a question.
Okay.
I just don't see where the ethyl came from.
Wait,
The
say
two
again?
ethyls on the right.
I'm sorry, I
Off
didn't
the
understand you.
oxygen. The ethyl off the oxygen, I don't see where it came from. Where did it come from?
These 2 carbons came from the ethanol that we added to this. It's not shown in the picture.
Oh, okay.
So I started with this dicarboxylic acid, right, and I added an alcohol to it, right? So carboxylic acid plus alcohol makes an ester. The ester I'm making uses ethanol as the alcohol. So that's where these two carbons came from. And of course I added another molecule of alcohol to the other side, and here's the other one.
Shouldn't there be a negative charge then?
There's no
Right.
negative charge because we don't just lose this H, I lose the entire OH. Right? We're not doing the deprotonation here. We're losing the entire OH along with the H from the alcohol to make water. And this carbon has now lost a bond, and the O from the alcohol has lost its bond, and they bond to each other. Right? That's this here.
I have a question.
Uh-huh.
Sorry if you just said this, but if you were to have like an ethyl on one side and then a methyl on the other, so let's say on the right O, you just had one line, and then on the left O, you kept it the same, it would be methyl ethyl.
It would be three separate words, but you would put them in alphabetical order. So it would be ethyl, methyl, butane diurate.
Okay.
Right.
Okay.
But you're
Thank
right. It would have three separate words. One of them would be ethyl, one of them would be methyl, and we put them in that order because that's alphabetically. They're still separate words. We just list them separately. And then the parent name would still be butane diurate.
Do you separate them with a dash, the
You
two
separate
words?
them with a space. They're separate words.
Oh, okay.
So this is the first molecule you've seen, other than the simple one that said acid after it, right? But these are the first ones where each word actually has meaning.
Gotcha. Thank you.
Okay, good. But if they are the same, you can call them diethyl like this. Okay, so let's try naming these down below. You got the rules down. So these down below, let's find the parent chain, and like all your other ones, we first find which highest priority thing is there. So what do you see on the left?
Carbonyl?
Or other than a carbonyl, be more specific, because lots of things have carbonyls, right? Is it an aldehyde? Is it a ketone? Is it a carboxylic acid? Is it an ester? All those have carbonyls.
It's an ester.
It is an ester, right? So esters have equivalent priority to carboxylic acids because they essentially are carboxylic acids with another group on it. So again, this is our highest priority thing, but it's not exactly a carboxylic acid, is it? It's an ester, so we're going to have an additional word out there. So ignore this thing on the right for a second and name the carboxylic acid that this came from. What's the longest chain?
Propanoic acid.
It would be propanoic acid, but again, this is an ester, so we change the ending, we drop that word acid, and we call it what?
Propanoate.
Propanoate, exactly. So the propanoate is our second word, right, our final word, and what's the first word going to be?
Methyl.
Simply methyl, right? And they are separate words, make sure you leave a space. So methyl, propanoate. Right? So, oops. Just like that. The one on the right is also a methyl propanoate. Can you see that? It's 1, 2, 3 carbons, and then 1 carbon over here. The only difference between these two is what?
Bromine.
Bromine and
Chlorine.
it's wearing some halogens, right? We put some jewelry on this molecule. These are just substituents, right? These are substituents you've seen before. This one's going to be called a what when it's a substituent?
Bromo.
A bromo
Chloro.
group, and this will be a chloro group. You've seen this before. The reason I'm bringing this molecule up is because you have to put the substituents on the right parts of the name. The bromine is on which part of this molecule?
The alcohol.
It's on the, what was an alcohol, it's on the methyl part now, right?
Yeah.
So instead of calling this methyl propanoate, you have to put the bromo on the methyl word. It doesn't go on the second word, it's on the first word. So the first word of this thing should be called what?
Bromomethyl.
Bromomethyl. And that's the entire first word, just bromomethyl. Right? The second word, instead of being propanoate, has a substituent. So what is the second word of this thing?
Chloropropanoate.
Be a little more specific. Tell me where it is.
2-chloropropanoate.
2-chloropropanoate, right? The propanoate, it's by default on number 1, but the chloro is on number 2. Why do I need the 2?
Could have been on 3.
Could have been on 3. The bromo couldn't have been anywhere else and still be a part of this word, right? If the bromo was over here, it'd be on the second word. So when you do this, the first word is bromomethyl. There's a space. And then the second word is 2-chloropropanoate. So you put the substituent names on the appropriate words, depending on where they are in the molecule. Right? If there were a bromine over here instead, what would this name of molecule be? If this were a bromine instead,
Bromopropanoate.
it would be a 2-bromopropanoate, right? You don't call this dibromo because they're not on the same word. So you treat them separately. Everybody okay with that?
Yes.
So wherever the substituents are, I just use bromine and chlorine as examples. There are other substituents, of course. But wherever they are, that's where you locate them in their name, right? So they're unrelated to the other word.
Quick question. On our priority list, we're going to put esters next to carboxylic acid.
Yes. So if you see a carboxylic acid and an ester in the same molecule, which I won't do that to you, they're of equal priority, right? So I won't do them both at the same time. You'll either see it as an ester or you see it as a carboxylic acid. So whichever of those you see is your highest priority. Okay, so remember before when I told you you mix a carboxylic acid with an alcohol to make the ester. And perhaps those R groups are part of a longer same chain. Right? We said it would form a what?
A ring.
A ring. And so those are going to be called cyclic esters, and they have names. They're called lactones. Right? It does not make them a ketone, although it resembles a ketone, but it's not a ketone. Right? They're esters. So you take the carboxyl group of 1, right? And on that same molecule somewhere else is an OH, and those two are going to react. Right? So before you look at the answer over here, or maybe look at the answer and help you figure it out, this OH is leaving, right? We said that the carboxyl group's OH leaves, along with this H to make the water. So what must this O bond to then?
The carbonyl carbon.
The carbonyl carbon, right? This O is going to make a bond to the carbonyl carbon. So it's kind of hard to draw that here. It'd be a big curved line, right? It's difficult. So when you do this, the easy way to think about rearranging it, how I drew it over here, is to start counting carbons. So this is the carbonyl carbon. That's number 1, 2, 3, 4. Right? So this is a 4-hydroxy, because that's a substituent, butanoic acid. Then I know number 4's carbon is going to be bonded to this O, and I know this O is also going to be bonded back to number 1. So how many members will be in this ring? I didn't say carbon. How many members will be in this ring?
5.
5. 4 of them will be carbons, right? The carbon 1, 2, 3, and 4, because that's where the OH is. If it had more carbons, they would not be in the ring. And then the O of this OH will be in the ring as well. So 1, 2, 3, 4, 5-membered ring. So over here, I would just draw a pentagon, right? 5-membered ring, erase one of the corners and make it the O. Right? So then this is carbon number 1, 2, 3, 4, and if there were 5, 6, 7, 8, 9 carbons, it'd still be attached right here. But the O is now bonded back to carbon number 1, making it a 5-membered ring. If this had been on a different carbon, like the one below, it's on carbon 1, 2, 3, 4, 5, then it would make a 6-membered ring, because it's the 5 carbons plus the O in the ring. The OH is not necessarily always on the last carbon. I just use these two as simple examples.
The oxygen on the carbonyl never leaves.
The oxygen for the OH doesn't leave. The OH over here leaves, just like we've done before. This OH leaves with the alcohol's hydrogen to make the water. The alcohol.
Okay, so that oxygen stays in the same spot though, like the carbonyl oxygen?
Yeah, the carbonyl oxygen is exactly the same. It didn't move.
Thanks.
But the carbon of the carbonyl is now bonded not only to the number 2 carbon, but to the O wherever it was. So we have this new bond.
I have a question.
Uh-huh.
Are the letters just acting as numbers? Like, is there a reason that they're letters?
Yes, that was my next point I was going to make. So the Greek letters here are an alternative numbering system. Okay, so we have our normal numbering system where it's this is number 1, 2, 3, 4, 5, 6, all the way to the end of the chain, right? But we also have a numbering system for this where if you have a carbonyl in a molecule, this carbonyl is called the carbonyl carbon. It's number 1, but it also gets no letter. It's just called the carbonyl carbon. Just like this is the carbonyl oxygen. The second carbon is called the alpha carbon, first letter of the Greek alphabet. Right? And then the third carbon is called the beta. The fourth is called gamma. If there were a fifth carbon, like this one below, it's delta. You just go down the Greek alphabet. You guys may be used to the uppercase Greek letters in the sororities and fraternities on campus, but these are the lowercase Greek letters that we use for this. So alpha, beta, gamma, delta, epsilon, and all the way down to Greek alphabet, as far as you'd like to count. Okay, so alpha is number 2, in fact, because this one doesn't get a letter. So the reason we use these sometimes is I call this a gamma lactone. And by gamma is the 4th carbon, so because it's the 3rd letter. So 1, 2, 3, 4, gamma is number 4. I know that the O, when I say gamma lactone, I know the O was on the gamma carbon, or the 4th carbon. You could also call this a 4 lactone. Right? That just tells me where the O is located. It's on carbon number 4. So when I say 4 lactone or gamma lactone, or in this case delta lactone, I know how big the ring is. Because if it's a gamma lactone, there's 4 carbons involved, the carbonyl carbon, alpha, beta, and gamma, and then the oxygen making it a 5-membered ring.
Is it okay if we use numbers, or would you like us to use
It's
this?
perfectly fine if you use numbers, but you may have to recognize this wording on an exam.
Okay.
Okay, so let's actually name these. This is just a gamma lactone. It doesn't describe really all the... What if this had other stuff on it? This doesn't describe it. This is a family of molecules. All right, so we're going to rename this in its appropriate names. So when you make this lactone into, or you make the carboxylic acid into a lactone, in other words, we're making a cyclic ester, we don't change the ending like we did before. We remember we got rid of the oic acid and changed it to O8, right? We got rid of that ic acid and added O8. Here we get rid of the oic and add olide because they're in the same molecule. So olide is the prefix or the suffix for lactones. So how do I do it? Let's take this one. It's 1, 2, 3, 4 carbons long. Right? And if it were longer, this is an exception to our rule, we can keep counting. So 1, 2, 3, 4, and if it had more on it, it would be 5, 6, 7, 8, 9, whatever. The reason I can keep counting is because I can, you're probably thinking, wait a minute, you broke your rule of going in the ring and outside of the ring. But this is not a carbon-only ring. It's a heterocyclic ring. So I'm able to continue, right? Because this is not a carbon. I didn't make a carbon-closed ring. So 1, 2, 3, 4, and if it keeps going, 5, 6, 7, whatever. So this one's only 4. So the parent name would have what word in it? 4 carbons long. Just like here.
Butane.
Butane. But instead of butanoic acid, I changed the ending to what?
Butanolide.
Butanolide. Exactly. So butanolide. Okay, so I just replaced the OIC acid with olide. If I put a 4 here. You could also have left a gamma there if you'd like. It just tells me where the oxygen was. So wherever the hydroxy group was, that's the number that goes here. Because that's describing where the O is now. Right? So whatever number was in front of the hydroxy is what's going to end up here. So it's pretty easy to convert the name. You guys do the bottom one. What would this be called?
Five pentaolide.
Keep all the syllables.
Pentanolide.
Right, 5 pentanolide, exactly. And you could replace 5 with delta if you like. So 5 and delta mean the same thing. So 5 pentanolide or a delta pentanolide. If this is longer, right, so imagine if there were an extra carbon sticking up here, an epsilon carbon or a 6th carbon. Right, so 1, 2, 3, 4, 5, 6. What would the name of this thing be on the left if this had another carbon sticking off here?
Five hexanolide.
Well, the one on the left here, would it still a carboxylic acid?
There'd be a methyl on it.
It would not be a methyl. The carbon chain would be longer.
Oh.
Right? So what
5-hydroxyhexanoic acid.
Right. If it had one more carbon, it would still be 5-hydroxy because it's still on number 5. This would not be a methyl group. It would just make the chain longer. So it would be a hexanoic acid. And then if I did that into the ring here, it would still be the same size ring because the ring's determined by where the OH is. And it would still be another carbon sticking off right here. Right? It wouldn't be a methyl group. It would still be part of the main chain, just like before. Right? So what would its name be if it had an extra carbon here? You said 5-hydroxyhexanoic acid, and I agree. What would its name be here if it had another carbon sticking off?
5-hexanolide.
Right. It would still be 5, because that's determined by where the hydroxy is, but this would be a hexanolide. Even though it's still only 5 carbons in the ring, right, it would be a hexanolide because of the extra carbon. And if this had, 5 more carbons off of it, it would be a decanoic acid, right? And over here it would be a 5-decanolide if it had 5 more carbons.
I have a question.
Uh-huh.
I'm still confused. Why would the methyl become part of the main chain? Because if the O wraps around and goes to the carbonyl carbon, how does that?
Because this O is not a carbon.
Yeah.
That means I don't have a closed carbon ring, so there's no reason to stay within a ring. You can go in and out of the ring, as long as you don't have a closed carbon ring.
Okay. Okay.
It is sort of an exception to what I told you earlier, right? That we don't go in and out of the rings, but when it's heterocyclic rings, you can.
Okay.
But this conversion should be rather simple. Find the longest chain. The position of the OH determines this number here, or this letter here. But the longest chain still continues, and it would still continue off of here. If there was something sticking off here, that would have been a substituent here, right? It wouldn't have been part of the main chain anyway, so it would still be a substituent. So if there were a carbon sticking off right here on number 4, it'd be a 4-methyl over here in the name as well, and it would still be a 4-methyl here. Okay, so draw out some examples or look at some of the practice tests and look online for some practice problems, and you'll be able to do a lot of these. But they're all similar. Okay? So let's look at this bottom molecule. This is called dipetolactone, and we don't have a receptor for this, but felines generally do. Right? And they tend to go crazy over it. Some species or some breeds a little more than others. But I don't want you to name this. I don't want you to be able to come up with a dipetolactone or other IUPAC name for it. I want you to look at a molecule like this and see this is a lactone. What gives it away? Let's go back and look at lactones. This is an ester arrangement, right? So COOR, right? It's not an OH anymore, so it's like a carboxylic acid, but it's got another carbon on the other side of the O. That was what we said was an ester. C double bonded to O and then OR. But this is continuing back to the same carbon. It's in a ring. So this is a cyclic ester, which was a lactone. This one has that same functionality. There's a COOR, but it is continued in a ring. Right? So this is an ester. It's a cyclic ester, therefore it's a lactone. And that's all I want you to do with molecules like this. That no way you're going to name this right now, but I want you to recognize it is a lactone. Everybody okay with that? You're not going to have to name this at all. I just gave you the name for your information. But be able to recognize this as a lactone. Go ahead.
I'm sorry. Could you actually explain that one more time, where it is?
Why this is a lactone? Because it has a carboxyl group that is no longer an OH, right? So it's COOR this time. Right?
Gotcha,
That's what an ester is. But just a COOR doesn't make it a lactone. The fact that this carbon and this carbon are part of the same ring makes it a lactone.
Gotcha.
Right, so the carbonyl carbon and the carbon on the other side, right, making it an ester, are part of the same ring. Who cares that it's got a double bond and other foliage attached to it, but they're part of a ring, which makes it a lactone. Right? So be more specific. What kind of lactone is this? Is it a beta lactone? Is it a delta lactone? Is it a gamma lactone? Or if you'd like to use a number, you can do that. So this is carbon number 1, because that's the carbon.
A gamma lactone?
It's a what?
A gamma lactone?
How did you get that?
Because it has. Oh wait, no. I lied. It's a delta lactone.
It's a delta lactone. So here is carbon number 1, 2, 3, 4, 5 is where it is. So it's a 5 lactone or a alpha, beta, gamma, delta. Any questions on this part? Okay, so here's some other esters that you're going to deal with in lab, if you do that lab this semester. And recognize each of these as an ester. And you should be able to pull apart the two parts that made it, the carboxylic acid and the alcohol. So let's look at one up top. How about the pair, the one in the middle at the top? So in this case, this molecule that gives the flavor of pear, right, these esters generally have fragrances or flavors. What was the carboxylic acid used to make this? And how do you figure that out?
Ethanoic acid,
It was ethanoic acid. How'd you figure that out?
because it's a 2-carbon chain.
Right, so you locate the carbonyl carbons, right? And at that point you count how many carbons are in that chain. So 1, 2. What was the alcohol used to make this?
Ethanol?
1 propanol.
Right.
Oh, propanol. Yeah.
Right, it's 1 propanol. Be careful, it's not 2 propanol because it's very specific. There's 1, 2, 3 carbons, and the OH that was originally there was on number 1. Right, so this is made from...
Wait, why would you have to put 1 though? Like, I know you wouldn't name it as an alcohol, but
Because if the O were on number 2, like a 2 propanol, this arrangement here would be
Oh.
quite different.
oh duh.
It would look like
Yeah.
this.
Okay, thank you.
Okay. How about, let's do the one on the right. What is this one? This is the flavor of apricots. So what's the carboxylic acid used?
Butanoic acid?
Butanoic acid, right? 1, 2, 3, 4. Very simple. And the alcohol that was used? Just cover all this up and put an H there, and that'll look like the alcohol that was used.
2 pentanol?
So it's
No.
so the carbon
2
chain would be
butanol?
the carbon chain would be how long? 1, 2, 3, 4. This is not in the main chain. Or if you count 1, 2, 3, 4, this is not in the main chain.
It'd be 3-methyl-butanol.
So 1, 2, 3. One of these is a methyl, but butanol. But I need to know where the OH is.
So 3-methyl butane-1-ol.
Or 3-methyl-1-butanol. Right. You can put the 1 in front of the all if you'd like. That's the newfangled way to do it. Or you can put it in front of the butanol. Okay, good. So that's what you'll use in lab. You'll grab several of these. In fact, the one you're going to make the most, I think you're going to do this one at the bottom right in lab because it tends to smell okay. None of these smell bad, but some esters do. So what's the carboxylic acid used to make the methyl salicylate down here, or oil of wintergreen? I told you wintergreen was not the same as the other molecules you made earlier. So what carboxylic acid was used to make oil of wintergreen? It's not spearmint. It's a different molecule.
Some type of like benzoic acid.
It's almost benzoic acid, right? If this OH weren't here, it would be benzoic acid, right? So what would it be called?
2-hydroxy-benzoic acid.
It would be a 2-hydroxy benzoic acid. That's absolutely right. Right, which is also known as salicylic acid. That's often found in astringents that you find in face cleaners and anti-acne medication and things like that. But then what alcohol did we react that 2-hydroxy benzoic acid with?
Is this ethyl, methane?
Not methane, but
1-methanol.
do I need the 1?
No,
No,
just methanol.
It's just methanol, right? It's just 1 carbon. So it's with methanol, which is our wood alcohol. So two things that seem like they have nothing in common with flavors whatsoever. Salicylic acid, which is used in astringents and face cleaners, and methanol, which is our wood alcohol. If you mix those together and make an ester out of it, it makes wintergreen flavor, right? Which is totally safe, right? You can smell this all you want. Right? So somehow this combination looks a lot different to our body than the parts individually, and that's true. We also can break this bond at some point as well. Change it up a little bit. What's the difference between that molecule and the one in the middle that gives grapes a flavor? This is artificial grape flavoring, right? But it tastes like grape. This was in all those purple drinks that you had as kids.
You just replace the hydroxy with an amine group.
Right, so I'd have an amino group, right? We haven't covered those yet, but it's just very slight change. And this gives a flavoring for grape, right? And what about the one on the left? This will be your favorite, right? The peach artificial flavoring. I changed it up here. Be careful of the orientation. What was the carboxylic acid used here?
Ethanoic acid.
Right, it's on the right this time. It's not on the left. You got to be careful where this O is. So all of these are listed on the right, but this one's flipped around on you. So this is the carboxylic acid, ethanoic acid, right? And what was the alcohol used? You may have a little trouble naming this one.
Methanol.
It was what?
Was it methanol?
It's sort of methanol. It's got a substituent.
Phenylmethanol?
It's a phenyl methanol. That's one way to name it, yes. That's the way I would have you name it for our rule so far. So parent chain is just this guy, right? The OH on the carbon. So it's methanol with a phenyl substituent. So phenyl methanol. All right. Very good. But when this is a substituent in the ester name, what do you call it?
Benzyl.
That's a benzyl ethanoate would be the proper name of this. Or acetate's the common name there.
Well, isn't that a toluene though? Like that on the...
A toluene would be this benzene ring with just the methyl on it, no oxygen.
Okay, thank you.
But the OH is of higher priority, right? Alcohols are of higher priority than all those other things. So we named the methane or the methanol as the parent chain.
So just to clarify, benzyl's just a substituent for esters?
No, benzyl is when you have a benzene ring and one other carbon, and that's how it's connected as the substituent.
Okay, thank you.
If it did not have this carbon here, it would just be a phenyl group as a substituent. Right? Let's say that wasn't there. This carbon was not here. This would be a phenyl ethanoate or phenyl acetate. What would the alcohol have been that you used to make that? If this carbon, imagine it not being there. So this O is connected directly to the ring.
Would have been a phenol.
It would be a phenol, exactly. Okay, good. So you guys, I think you got those. Try some of these other ones in here and see if you can figure out what it was made from. Right? And then there are plenty more fragrances that you can look up online. So these are all a lot of artificial flavorings here. Okay. And here's another molecule that I'd like you to recognize and answer the question, what functional groups do you see? So since we're talking about esters today, is this an ester? It's a very big molecule, so look for an ester in there.
Yes.
Is the bottom left portion an ester?
Right, so it's this carbonyl, right? C-O-O-R. Right, so if this didn't have another R group, it'd be a carboxylic acid, and you could have picked that out easily. But because it continues to another R, this is an ester. Can you be more specific about it being an ester?
It's a lactone.
Right, it's a lactone, right? It's a very big lactone, right? So if you could count down the Greek alphabet, this one doesn't get a letter, but alpha, beta, gamma, delta, epsilon. You keep going around, and you don't have to memorize all those Greek letters unless you really want to. But when you get to this position here, that would be the letter you'd put there. It's number what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lactone is what it would be called. Right? I don't want you to try to name this. It's quite large. It's got lots of substituents. But I want you to recognize it is a lactone. Is it a very big lactone or a very small lactone?
It's a big one.
It's big. It's out of number 13. So what kind of prefix would you put in front of it to indicate that it's large? What's a word that means large?
Mega.
Mega would be cool, right? But what's another similar word?
Macro.
Macro. And what ending did we put on lactones?
Olide.
Olide. So these are called macrolides. So if you hear the term macrolide antibiotic, which you're going to come across in your careers in medicine, that's describing this style of molecule where there's a big lactone ring. So it's a cyclic ester with a very big ring. Right? So these are macrolide antibiotics. And originally they were discovered in fungi. Right? They make these molecules to kill bacteria. Fungi do not eat bacteria, but the bacteria and the fungus are competing for the same food source. So this is a chemical warfare. The fungus is killing its competition for the food, right? For the chemicals in the environment. So these are macrolide antibiotics, and we've discovered them along with things like penicillin, which is a different type of molecule. It's very, very similar, though. It's not a macrolide, but it's similar. We'll talk about it when we get to our nitrogen talk later. But these fungi are making these things, and of course, as humans, we've taken them and modified them heavily. Right? We can change. You notice this is a sugar out here. Here's another sugar. Right? So we've got all these carbohydrates attached. Right? You probably could figure out which carbohydrate this might be. It's okay if you don't. I'm not going to ask you that because they're highly modified, right, with the methyl groups on them and such. But the fungus builds this molecule, puts these sugars on it, and this molecule actually kills bacteria. And as humans, we come along and we say, what if this wasn't a methyl? Let's change this to a propyl group or an ethyl group, or let's put a benzene ring on it right here. And this is what the organic chemists do, commercial organic chemists that work for pharmaceutical companies. They start modifying this, and maybe one of their modifications makes it work even better, or it's less side effects, in humans, or it's safer to the liver, or maybe it's worse, and we don't choose that one. Right? So whatever they do to it, they modify these things, and that's the new drug that comes out. So if you hear about a new macrolide antibiotic, they likely took this base molecule and changed something about it. And it may have some more benefits. Usually it's minor benefits, but they'll certainly advertise the heck out of it to say this one is longer lasting, or this one has this added feature, and they'll spend more money on the advertising than they will on developing the drug. And that's how we come up with new antibiotics. And of course the bacteria are generally one step ahead of us. We've seen this before, or we have a way of fighting that, or we mutate to make ourselves immune to it. It happens all the time. Right? And then lastly, I want to talk about taking these esters that we just built. You'll also do this in lab with your methyl salicylate or your oil of wintergreen. So this represents your generic ester, right? It's R on this side, some R group on this side. They may or may not be connected. Who cares? It's an ester. And you undo the process. So instead of doing esterification, we do hydrolysis. So here we're adding water back. And remember, when we made this, we lost the water molecule, so we're putting it right back. This carbon O bond is going to break. The OR here gets the H from the water and becomes an alcohol, so this H should be blue. So draw that in blue right there. This is a mistake in the figure. So this should be a blue hydrogen because it came from the water. And then the carbonyl carbon gets the OH that's left over from the water. This is exactly the opposite of putting it together. If you turn this arrow around and go this direction, of course this would be a blue H, this would be esterification. It's simply undoing that bond. It's fairly easy to do. You just heat up the molecule, add a little water, maybe a little acid to change the pH of the solution, and the ester will fall apart. Sometimes it's broken by an enzyme, but esters fall apart readily. They're very easy to break. So if you have an oil of wintergreen and you leave it around in the sun or the heat, or because it's in your perfume, or if it's in whatever sample you have, it's a bunch of esters that are making up the fragrance that you have. If you leave it in very warm conditions or out in the sun or a hot room, likely a lot of those molecules are going to fall apart and it won't have the smell or fragrance that you originally intended. So if you keep your perfumes nice and cool and keep water from getting in there, because clearly water breaks up this bond, then it'll last longer. So keep them dry and keep them out of the heat, or out of sunlight for sure. And at the bottom, instead of using under acidic conditions like I described here, we do the same reaction under basic conditions. So the only difference is when we break this bond, it's just like this one, we're going to break this bond. The OR that leaves gets the H from the water one more time. It makes an alcohol, no problem. And the carboxyl group, once again, gets the OH from the water, making a carboxylic acid. But under basic conditions, carboxylic acids react with bases, we saw this last time, to make a salt. Okay, so all we're doing is removing this H once it's formed and putting it with the sodium to make this carboxylate salt. Right, this is how we make soaps. So instead of doing a regular old ester here where it's something really short, and this R group is really long, like say it's 17 carbons long here. Then I have a very long, what we call fatty acid, which we'll talk about in the next exam. So a fatty acid connected with an alcohol here, and if I add a base to it and break that bond, I'll get my fatty acid bonded to the sodium, which will not be soluble in water because it was a long carbon chain, and the alcohol will. Generally, the R chain over here is rather short. So this R chain will be soluble, and I can pull that away. And this is how we used to make soaps in the old days. Now, my grandfather used to do this. He would take a fatty acid, right, ester. Generally, you get this from butchering an animal. You didn't waste anything. So if they were leftover fat that you didn't want to cook, so they butchered a pig, and there was lots of fat left over, which was mostly these esters, with the alcohol here being the glycerol. They added a base, which you would go to the hardware store and buy. So lye you would buy in a big bag, and you sprinkle it on this fat in a big box in the yard. And of course, you add some water, right, which you get from the garden hose. And you get a big wooden stick, and you stir it all around, and it smells wonderful. You can smell the sarcasm. All right, you stir that up for a while, and let the sun bake on it to provide the heat. And eventually, the alcohol that forms floats to the top, and the carboxylate here, the sodium carboxylate, is sinking to the bottom because it's not soluble. And if you remove the alcohol, right, you grab your wooden paddle and scoop off the goo on the top, all this alcohol, then that forces the reaction to go forward even more. It's Le Chatelier's principle. You guys talked about that in your first chemistry course. If you remove a product, you tend to have the reaction go forward. And if you add more substituents or more substrates on this side, you tend to drive it forward. So you'd add more lye, add more water, remove the alcohol. And of course, eventually the reaction will come to completion when you run out of the carboxylate ester and let this dry and bake in the sun. What's left over is basically soap. You get your pocket knife out, you carve out a little square, and that's soap. It's not very good soap. My grandmother would not let that in the house. It would be great soap for cleaning tools in the shed or cleaning tractor parts or something like that, or maybe washing your hands outside, and then coming back inside and washing it with a much cleaner soap, right? Because this is just a working soap, right? It's very crude. It's the same way soaps are made today. It's just under better conditions. They're not poured in a box in the yard, right? So they add fragrances and other things to them. But those fragrances you add to soaps are likely added after the reaction is done, especially if they're esters, because they would have been destroyed in the process. Right? And then one last topic.
I have a question.
Go ahead.
It was on the part on the side before. Why is the first one a generic ester and the second one a carboxylate ester?
Well, that's the same thing. So this is an ester, right? Because there's a long chain here and a chain here, however long they might be. And this is a carboxylate because I still don't know how long this chain is. Remember, the carboxylic acid becomes a carboxylate, and that named this part of the molecule. It's just the same name over and over.
It's the same one for the one that's up top, right?
Right. So this is also an ester. Right? It's called a carboxylate ester because it's got a carbon in it. You don't know any other type at this point, so we could have phosphoesters and other types, which we haven't talked about. But you can just think of this as ester.
Okay, got it.
Right. I didn't mean to confuse you with carboxylate because there are other types of esters, like phosphoesters, but we're not going to talk about those yet. Right. The very last thing is if we make a thioester. What does thio mean? What did that prefix refer to?
Sulfur.
Sulfur, right. So here I'm making a thioester. Here's another thioester. And what's really different between a regular ester and a thioester? What's the only change you see?
Bonded through a sulfur instead of an oxygen.
Right. There's still a carbonyl. That O is not changed. But what normally would be the OR is now an SR. So this O has been replaced with sulfur. Where did this sulfur come from? Which of the two original components had this atom? Was it the carboxylic acid or was it the alcohol?
The alcohol?
The alcohol, right. So remember, when we had a carboxylic acid, we lose its OH and it's gone. And then the alcohol that comes in, if it's an OH with an R group attached to it, becomes attached through its O. So this S, if it's in a thioester, must have originally come from the alcohol, not the carboxylic acid. If the carboxylic acid had an S here, if this were COSH, that SH would also be lost. So the carboxylic acid cannot contribute this atom. It must come from the alcohol. So if it's an S, this must have originally been a thiol, which is an alcohol with an S instead of an O. So when you look at something like methyl thiopropanoate here, what components were used to make this? Although the thio is now in this part of the name, because that's described all of this, and this part's described as methyl, this sulfur originally came from the alcohol. So what was the original two components of this? The carboxyl group had 1, 2, 3 carbons, so it was simply propanoic acid with no sulfurs on it. And this S, since it's in this position, came from the alcohol component. So it was a 1-carbon alcohol with a sulfur. So it wasn't just methanol, it was thiomethanol, or methane thiol, is how you say it. Okay, so I want you to know that this position, whether it's an S or an O, comes from the alcohol component. So if you look at a lot of your questions, I ask, what was used to make this ester? Right? So a thiocarboxylic acid could have been used, but I would have lost its sulfur anyway, so it didn't matter if it had a sulfur or not. But if I just use a regular alcohol, I will not get an S here. It must have had a thiol to put an S here.